Who's my favorite student? Oh, my favorite student is Anne. This quiz, everything is 1 mark, and I'm going to be fussy, all or nothing, because it's fairly plug and chug. So number 1 asks how much work is done. Well, work is force times distance. So it's going to be 767 times 28. No idea what that is. 767 times 28 is 21,000. I'm going to write 21,500. Units, joules. Again, if you haven't done the quiz, don't be foolish and just copy this out and think that's what I'm looking for. I know who you are. I can see when somebody is obviously blatantly writing down everything that I'm doing and then they're going to hand it. And don't be that person, please. That would be silly. Power. I'm fine if you said 21,476. That's good. Power is work over time. I'm going to write, in fact, Colton, I'm going to write 21,500, but you know I'm using my answer button here. Divided by 58. Not times, Mr. Dewick. Divided by 58. Did you get 370 watts? How much work is done by a forklift raising? You know what? Raising is a trigger word like lifting. The work is going to be MGH. And we learned yesterday that another way to think about that is to say you're giving that object some gravitational potential energy. It's going to be 688 times 9.8 times 2.8. I get 18,800, I'm going to go 18,900 joules, is that right? Again, if you didn't round off, that's fine. Are you all capable of doing that much work? Yes, absolutely. Yep. Except probably you would have to come up with a way to increase the distance, maybe with a pulley system or with a ramp, in order to reduce the force required. But absolutely. Now, the real question, because remember, work is just how much energy transfer. If you spread that out over a long time, that's not a problem. All of you are capable of doing that much work. If I make you do that work quickly, well, that's power. So if I make you do that work in 73 seconds, that's a little less likely. I'm going to write 18,900, but I'm going to use my answer button. 200. Well, you know what? All of you are capable of putting out about 259 watts. I would take 260 as well. You couldn't do it for very long, but you could. So raising that in 73 seconds, 2.8 meters. 2.8 meters is about the height of my ceiling. You know what? If you had a good pulley system, you could do it in 73 seconds. Yeah, it's doable. Work a vector or a scalar? Oh, I heard both, vector and scalar. Which one's correct? Scalar, absolutely. No direction, it's a scalar. What are the units for work? Or, because work is force times distance, I would accept Newton meters, because that's force times distance. Or, because F equals what? Or, because F equals what? You could actually go m kilogram meters per second squared meters, which would be kilogram meters squared per second squared. Almost all of you did that. If I turned this into a multiple choice question, I don't think I'd have that to pick from. I'd probably have that to pick from. But I wouldn't go 3 or 4 levels deep. I think going 1 level deep into the units is totally fair game, Brian, but I wouldn't go 3 or 4 levels deep. Because power is measured in watt. Well, I would absolutely take watts. But that's also a joule per second. That's probably what I would give you on a test. But since a joule is that, it's also going to be a kilogram meter squared per second, which actually makes that a kilogram meters per second, meters squared per second cubed. I'm not going to go that far. I'm a nerd. I love diving all the way into the units to see what they're made of. But certainly asking you to go one step into the units, to me, that's fair game. Okay? What is the minimum power? I said, okay, power is going to be work over time. If you're climbing stairs, the work you're doing is MGH over time. Then I said, nice try, Mr. Dewick, 21 centimeters, that's 0.21 meters. And so that's going to be 64 times 9.8. The height is 82 times 0.21 divided by 83. 64, not divided by, times 9.8 times 82 times 0.21 divided by 83. Did you all get 130 watts? 130.1, 130 watts? That's not a very big wattage. You know what? All of you could do that for a while, because 82 stairs in 83 seconds, Colton, that's almost exactly 1 stair per second. Most of you could keep that up for a few minutes. You'd get tired eventually, but not for a while. Number 7. Ooh, what's the power output of the motor? Again, we're lifting. There's my trigger word. So it's going to be work over time, and the work in lifting is going to be MGH. So it's going to be 25 times 9.8 times 24 divided by 32. 180, I'll go 184 watts. If you said 183.75, that's fine. Efficiency. So we said this. Efficiency was going to be, I figured because this is watts, I'm going to use power, not joules. So it's power out divided by power in. You know what? It's the smaller number divided by the bigger number. The bigger number is 244. The smaller number is 183.75. And then I would multiply that by 100 to turn it into a percent. So it's going to be that divided by 244. And I get 75.3% efficient, 75% efficient. Which that efficiency would tell me it was an electric motor, not a gas motor. And then I went, oh yeah, it did say electric motor, but I could have figured that out just from those numbers. Gas motors are way less efficient than that. Colton, last one. This was one I lifted kind of right from the last example in lesson 1. How much work did the applied force do? Well, the work done by the applied force is going to be the applied force times distance. The applied force is going to be 65 newtons. The distance is 14 meters. It does say it's horizontal. That's in the same direction as the distance. So my force and my distance match. It's going to be 65 times 14, and I get 910 joules of work. Now, if this was on perfect ice, all of that energy would have ended up turning into kinetic. The box would be accelerating, going faster and faster, and eventually you'd have 910 joules of kinetic energy. This is not on ice. We lost some of that energy to friction. So the work done by friction is going to be the force of friction times distance. I don't know the force of friction. I did a quick free body diagram over here. I said, okay, I got gravity down, normal force, F applied, friction in this way. I said, okay, friction is going to be mu times the normal force times distance. I don't know the normal force. Oh, but look. None of the force the same size as a normal force. I said, you know what? It's going to be mu mg/d, and now I could crunch the numbers. The work done by friction was going to be 0.25. What was the mass, Mr. Dewitt? 12 times 9.8, and the distance was 14. And I ended up with 411.6. I would take 412. I wrote the 411.6 because I figured I was going to be using it, and it was in joules. Technically, Colton, it's negative because you're losing energy. If you didn't put the negative there, I'm not going to take a half mark off. Where you have to be careful is when it asks for the net work done, the net work is going to be the 910 minus the 411. Was it 910, Mr. Dewick? Yeah. Minus what you lose to friction. So it's going to be 910 minus answer button. And that's where I get actually only 498.4 joules of energy actually went into making the box speed up. 411.6 joules of energy went into heating up the floor due to friction. If you had a really accurate digital thermometer or infrared thermometer, if you were trailing behind the box, you would see the floor had gotten warmer. Can you give yourself a lovely score, please, out of 13? If you need to lawyer with me, now is the time.